everyone. My name is Michelle Soupir. I'm a professor in Ag and Biosystems Engineering at Iowa State University, and I'm here today with Dr. Billy Beck and a PhD student in our department, Clarisse Siababa. And we are going to talk to you about one of our new projects funded by the USDA on wood chip bioreactors. So I'll start out by giving you a little bit of history. If you come to the state of Iowa 200 years ago, you would see a prairie and wetland system. But if you come today, you'll see a system that's highly agriculturally productive. And so the difference is that tile drainage has been installed. Tile drainage is very important. It's used to manage the moisture content in the soil to allow crop production, allows more farmable acres, and also allows heavy machinery to be able to gain access to the ag land early in the spring when crops would be planted. So this is very important, but it's also created a situation where water is able to move through the system, collect nitrate that may be in the soil due to the high nitrogen content of soils or due to nitrogen fertilizer or manures that have been applied to the surface to fertilize crops. And then from there, that nitrogen moves into the tile lines and can move off-site rather quickly. So one strategy to try and improve water quality and to treat that nitrate-laden waters is a wood chip bioreactor. A bioreactor is an edge-of-field conservation practice that can be installed between the agricultural land and the stream, and it's used to intercept that tile drainage and treat it before it's discharged. If you go out to the field and you want to look at a bioreactor, there's actually not very much to see. You might see a control structure to help manage the water flow, but everything that's happening is actually below the ground. When a bioreactor is installed, a pit is dug and it's essentially filled up with a carbon source. Wood chips are the most common source that's used in Iowa and much of the upper Midwest. And then a layer of soil is placed on top, and then it's going to be planted to some kind of prairie or vegetation. So the bioreactor, the water routes through the bioreactor. It can bypass the bioreactor during periods of heavy flow, and that's to ensure that water isn't backing up to the crop field and potentially damaging the crops. And then it discharges to the surface water. Most bioreactors are able to treat between 15 and 60%, meaning that that is the percent of nitrogen that is converted from nitrate, which is the harmful form that can cause a risk to public health, can contribute to downstream algae growth, and then remove it and convert it to nitrogen gas. The process that is taking place inside the bioreactor is what we're really interested in studying. So the bioreactor contains that carbon source, which is covered with microorganisms. It's actually the energy source for those microbes. And those microbes then work to take that nitrate and convert it to a harmless nitrogen gas. And that process is called microbial denitrification. As you can see, I'm not standing next to a bioreactor today. One really cool part about this project is that we get to think about the different trees and experience how we can manage our woodlands in order to provide the wood resources and carbon sources for the wood chip bioreactors. So today we're going to tell you a little bit more about our project, which is looking at those different carbon sources and specifically focusing on different types of wood species to try and better understand what are the extractives that are present in different wood species and how do they contribute to the microbiome or the community of microorganisms that all contribute to that denitrification process. An important aspect of this is, where does that wood come from? And so that is why Dr. Billy Beck is here, and he's going to talk to you a little bit about woodland management and how we can both manage our woodlands in a productive way and then use extra wood sources and wood chip bioreactors for combined ecological benefits.
Hey, I'm Billy Beck, Extension Forestry Specialist with Iowa State University Extension Outreach. And like Michelle said, one of the really neat parts of this project is connecting the water quality edge of field practice bioreactor facet with woodland management. We have over 3 million acres of woodlands in the state. It's a precious resource. Of those 3 million acres, 85% are privately owned. And that's important because we know from surveys and workshops that most of those acres under private ownership are passively managed. So Michelle talked a little bit about woodland management. So those acres are mostly passively managed. And in fact, we really need more of our acres to be actively managed. And I'll talk about what that means in a second. So forests, the 3 million acres of woodlands in Iowa, provide critical ecosystem goods and services to all Iowans. So things like clean water, clean air, wildlife habitat, and more importantly, the past few years, mental health benefits. And if we're not actively managing our woodlands are just not giving us the maximum that they can give as far as ecosystem goods and services. What we want to look for in this project is how do we sustainably source this material for carbon media for these bioreactors, but at the same time enhance woodland health by encouraging active woodland management across the state. And if you talk about forestry around the country and the world, markets tend to really help drive management activity. So one of the neat facets of this project is we're looking to see which woods or which blends of wood chips work best in bioreactors, and then how do we create markets for those species if they're not already a high dollar wood species in the state. So a lot of people think or ask, what is active woodland management? So in the past, 200-300 years ago, our woodlands were managed by a lot of natural and anthropogenic factors that we just don't have today. We've taken a lot of things out of the equation, things like fire and things like grazing from large mammals like bison and elk. And we've added factors such as invasive species, parcelization, other things that we can't really do a hands-off approach anymore. We need to be involved in our woodland stewardship and our management for these woodlands to be resilient and for these woodlands to give us all the ecosystem goods and services that they provide. And when I say active forest management, it's really a catch-all term. And it really is based on what you do in your woodlands management-wise is really based on the landowner or the steward's goal. There's no one right way to do it. So active management generally entails things like controlling invasive woodland species, planting new trees, reforestation, thinning our woodlands so that more sunlight gets to the ground, harvesting our woodlands for sanitation, for economic return, or to achieve a stewardship goal like wildlife habitat or water quality. So again, the neat thing about this is how can we connect bioreactors to woodland stewardship using that residual material that we harvest, perhaps getting a higher market value for it, so that would hopefully encourage more landowners to perform active woodland management across the state. In past extension events, we talked about the physical characteristics of the chips and how they vary by species and how that could potentially impact bioreactor performance. The main goal for today is to talk about the chemical differences between the species and how that might impact bioreactor performance. So we're going to explore some cross-sections of trees and talk about how chemical characteristics may vary based on the species, based on the size or age of the tree, and based on the growth rate of the tree. And these are all species that are involved in this research project. So this first one is probably Iowa's most famous species. This is black walnut. And I want you to notice two different things here on this black walnut. This interior dark area is what we call heartwood of a log. This outer ring, which has a light color here, is what we call sapwood of the log. Both are very important for the overall health, growth, maintenance of the tree. So heartwood is important because, for this project especially, heartwood, one of its main functions is that it houses byproducts of metabolism, which we collectively call extractives. So extractives, like you'll hear from Clarisse in a bit here, are kind of a catch-all term for things like fats, resins, terpenes, oils, and each tree species has a unique extractive cocktail mix housed within the heartwood. And it really is that mix is what gives certain species like black walnut its coveted color. It gives species like eastern red cedar that great smell. It helps with rot resistance. So a lot of cool things are derived from those extractives that are housed in that heartwood. We're interested in, if we chip this log up for these different species, how do those chemicals housed in the heartwood impact the microbiome of a bioreactor, thus impacting things like nitrate removal. So I want to point out three things here that kind of say that a tree is not a tree is not a tree, a log is not a log is not a log. The amount of heartwood, not only does the chemistry vary between species, but the amount of heartwood versus sapwood varies based on a number of factors between these species. So things like the age of the tree, the size of the tree, the growth rate of the tree, where we harvest the tree from, and how we process that material like chipping or tub grinder is going to impact how much heartwood versus sapwood we get in our bioreactor mix. And sapwood, very, very important for tree growth, but it doesn't house the extractives that may really impact the microbiome of a bioreactor. Sapwood is, as you can guess it, the living conductive tissue of a tree. So this is what brings the sap, which carries nutrients and sugar, up and down the tree for trees' overall health and keeping it alive. The heartwood, again, houses extractives, provides rot resistance, and is also for structural stability. In general, each species, when mature, has a set number of sapwood rings on the outside of the trunk. So that can vary. Some species, like this white mulberry here, only have a few sapwood rings on the cross section, where species like black walnut, green ash, and honey locust have maybe upwards of 12 to 13 sapwood rings on that outer part of the log. So species matters for the ratio of heartwood to sapwood. Let's talk about age though. As the tree gets older, this is the base. This is about a 25-year-old black walnut. And you can see it's got its set number of sapwood rings on it and a nice big proportion of heartwood in the center. This is the exact same tree on an upper limb, so this wood is much younger than this wood here. And you can see the ratio of sapwood to heartwood is very different than the base of that tree. So if we were to include this material, say in a chipping of using an arborist chipper where we use the log and the entire top of the tree, we would get a much higher content of sapwood in that mix than we would by just utilizing the log at the base. Also, the rate of growth matters. So this is a green ash. This is about the same age as this black walnut, but if you zoom in and look at the growth rings here, they're absolutely huge. That's going to impact the size of the heartwood in the center, the ratio of the heartwood in the center to the ratio of to the sapwood on the exterior. So growth rate really, really matters there. What's neat about these trees is that as the trees get older, the number of sapwood rings remain the same, but the heartwood material accumulates over time. So you're always going to have this area expanding and this area being, in general, the same number of rings. Larger trees are going to create more heartwood from their logs, provide more heartwood in their logs in general than younger trees. And that gets into like the processing facet of this study. If we were to use an arborist chipper, like you see in municipalities, they're going to throw the entire tree potentially into that chipper. So you're going to get a mix of heartwood dense material, the base, but you're also going to get a mix of a lot of sapwood dense material, which is the upper limbs. Now, if we used a tub grinder, which basically you throw everything in, they're kind of like an arborist chipper, but they can take on huge diameter material, you're going to get much older logs potentially being able to be ground up, and you're going to have, again, you'll have tops of the trees and all that kind of stuff that's got a sapwood component, but with those larger logs, you're going to have a high heartwood component to those as well. The way we process these trees, along with the age, the species, and the growth rate, really can impact the chemicals that we're providing to the microbiome in our bioreactors.
Hey everyone, I'm Clarisse Siababa, a Fulbright scholar from the Philippines, and it's a beautiful day to be out in the field because, I'm usually in the laboratory. But yeah, I'm very grateful to be part of Billy and Michelle's project on the wood chip bioreactor. And now, as Billy mentioned, the wood properties and extractives are very important because they can affect the denitrification performance of single wood species. Thus, it is vital to understand the impacts of wood extractives and how they can affect the nitrogen and nitrate removal of each wood species. For this project, we have identified 12 wood species that can be used as wood chip blends that would be used for our pilot scale bioreactor. And for the wood extractives, they are very vital because they are the non-structural compounds such as the phenols, terpenes, fats, fatty acids that can affect the denitrification potential of our bioreactors. So as Billy mentioned, the heartwood and the sapwood ratio can affect the denitrification potential, especially how many carbohydrates, free sugars are available in our wood species, and how can this affect the microbiome of each wood species. In the laboratory, we are using the wood species that have been identified based on their abundance, their vessel distribution, and their durability. The wood species that we have are undergoing cold water solubility extraction that you'll be seeing later on. For the cold water solubility, this is vital in the process of understanding the wood extractives, and they can be divided into three different compounds. The first one are the polyphenols or the phenolics, which comprised of the tannins, the gallic acids, and the ellagic acids, which can somehow interfere with the bioreactor performance. And that's one of the objectives of the project. We wanted to know if the tannins can really interfere with the denitrification potential of the wood chips. The second one are the free carbohydrates such as the glucose, galactose, lactose, maltose, and cellulose, to name a few. And as mentioned by Billy, these free carbohydrates can be found in the sapwood instead of the heartwood, because basically the ones that we can find in the sapwood are the carbohydrates that is used by the woods for their metabolism, while the ones that we can find in the heartwood are the ones that have been used and as products of secondary metabolism, called the secondary metabolites. And the third component of our wood extraction are the secondary metabolites, which includes the syringic acid, vanillic acids, and other polyphenols that can also interfere. It can either increase or decrease the denitrification potential of our wood species. So overall, we wanted to know how these wood extractives can affect the denitrification potential of the wood species that we have identified. Our project aims to understand the impacts of wood extractives on bioreactor performance by characterizing single wood species. 3 cores from individual wood species were collected using an increment borer. Lubricate the borer by applying beeswax to reduce friction and insert the bead at breast height. Then turn it clockwise to penetrate the tree to the center. It then produces a pencil-sized core spanning bark to middle of the tree. The annual growth rings can be used to estimate the tree's age. The wood properties and extractives may affect the species' denitrification performance. These 3 cores will be used to analyze some wood properties and extractives. The wood extractives were prepared using cold water solubility extraction. The cold water procedure removes part of extraneous components such as inorganic compounds, tannins, and sugars present in the wood. Approximately 2 grams of oven-dried grounded wood samples were weighed and transferred to a 400 ml beaker, followed by the addition of 200 ml deionized water. Then, water is slowly added to the ground wood samples in the beaker. Extraction is carried out at 23 degrees Celsius or room temperature with constant stirring using a magnetic tabletop stirrer for 48 hours. While the samples were being mixed continuously, a vacuum pump setup was prepared with filtered crucible in a 1000 ml filter flask with a rubber flange and a vacuum source. The vacuum is then turned on and the wood mixture with cold water was slowly transferred to the vacuum pump setup with addition of the ionized water to transfer all samples from the beaker to the filtered crucible. The setup was allowed to stand until all liquid filtrate was separated from the solid particles in the crucible. The wood extracts were collected from the filtrate and they are stored in the glass amber bottles. A portion of the extracts were aliquoted in amber glass HPLC autosampler vials, for submission to the Iowa State University Metabolomics Research Laboratory for GCMS and LCMS of free carbohydrates and HPLC analysis for tannins. The remaining wood extracts were analyzed for colorimetric total phenolic analysis and nitrate analysis at the Water Quality Research Laboratory.
When we first started working on wood chip bioreactors more than 15 years ago, we really just thought if you dig a pit, get some wood chips in there, as long as the water can flow through the bioreactor, we should be in good shape. But we're seeing so many differences as far as how different bioreactors perform, and we believe it really comes down to what is the wood product or that carbon source that's in the bioreactor. You can see so many different things can come into account if you think about different species of trees, different ratios of heartwood and sapwood, how the tree was processed either at a mill or was the entire tree chopped up and then used as the carbon source. There's so many different things. And then the color of the tree and those different extractives that can come out. So thanks for tuning in today, and we look forward to keeping you posted as we learn more about the different things, the different extractives that can come out of the wood, and then how they impact the microbial community that's actually the workhorse, that's actually doing the work, converting the nitrate to nitrogen gas.